My name is Robert Jellinek, and I'm coming from University of Wisconsin-Madison, and I'm going to be discussing our group's recent work on cloud billing systems. In the next 20 minutes, I'll discuss our motivation for studying cloud billing, our group's contributions, the details of our measurement study, our results, and our hope for future work on the topic. And in the past years, of course, as many have mentioned, cloud computing has grown increasingly popular, and businesses are turning towards it for its instant scalability, flexibility, and ease of use. And in the interest of maximizing these properties, there have been a lot of studies on the performance, reliability, and cost efficiency of the cloud, including in regard to spot pricing and reserved instances. But there's been little attention paid to the actual billing systems in play, in particular to the underlying mechanisms responsible for resource accounting and the corresponding customer-facing billing interfaces themselves. The fact is that a predominant pay-as-you-go cloud computing pricing model relies upon complex, large-scale billing systems, the mechanics and guarantees of which are still opaque to customers. So we see resource accounting as a fundamentally interesting challenge. And the question is, how can you track resource usage in real time and at fine granularity while maintaining accuracy and not hurting performance? It turns out that this is fairly difficult, as shown by our measurement study of several cloud billing systems. So that being said, even though it's difficult, we were able to determine certain things. We were able to disambiguate billing by reverse engineering the timestamps corresponding to various billing events. We were able to uncover bugs relating to race conditions in EC2, inconsistencies in the various billing interfaces provided by EC2, and found a rack space bug that caused overcharges in their persistent storage volumes. We were also able to detect systematic undercharging due to caching and aggregation in certain networks and storage platforms. And we were able to characterize the performance of billing latency, which we view as a substantial issue across all the billing platforms we investigated. So our main question during the study was, how accurate, timely, and predictable are customer-facing billing interfaces? We measured compute time, storage, network usage, and billing latency across three major cloud providers, Amazon Web Services, Google Compute Engine, and Rackspace. And we wanted to look at Azure, but due to time constraints, did not have a chance to. That's future work. So our general methodology for all of our experiments is as follows. First, we instrumented the provider's API calls to collect timestamps of all important instance lifetime events, largely by polling the APIs. And these APIs respond with an instance object that includes instance state. We then would launch an instance to execute the relevant workload to measure network, storage, or compute time resource usage. We then fetched OS-based resource usage data, either from procfs or netfilter or IP tables, which we used as the basis for customer-based knowledge about instance state. And remember, of course, the goal is to compare this customer visible information with what we're ultimately billed. Next, we terminated the instance after workload completion, maintained information about the timing of instance termination to compare with the final bill. And finally, we began polling for billing updates over all the measured resources. So there are a number of billing interfaces we could poll, in particular on EC2, and they all have different characteristics. All three providers offer web-based management consoles, while EC2 also provides programmatically accessible CSV files with varying granularities, and something called CloudWatch, which is a service that offers automated alerts when resources exceed a user-designated threshold. GC and Rackspace, though, currently only provide web-based GUI consoles for billing. So here's an example of the Amazon web-based interface, and for all of these, we had to come up with screen scraping mechanisms to periodically just poll these and get the information. Clearly not exactly user-friendly. So it turns out, though, we had to poll for billing updates for quite some time due to something we call billing latency, which I mentioned before. Now, billing latency, as we define it, is the time between when a resource is consumed and when the corresponding charge for that usage becomes visible to the customer. So ideally, the billing interface would reflect customer usage with low and predictable billing latency, so that the customer knows exactly how much she's been billed. But we found that's not actually really the case in practice. Bills were updated unpredictably, with long delays, and sometimes not even atomically. so that you could say bills for more than 1 hour of compute time could arrive in several stages, where updates would be separated by periods of several hours. This, by the way, additionally complicated our compute time billing threshold experiments, which I'll talk about momentarily, because it meant that we had to wait a really long time before deciding that all possible billing data corresponding to some period of usage had actually been registered. So we found that billing latency was long for every provider, some more so than others. These graphs here show the number of EC2 instances that experienced billing updates after a certain number of hours. So to read this, you'd look at it and see a bar at 8 on the x-axis with a height of 42 would show us that 42 instances exhibited a billing latency of 8 hours. For EC2 then, the web-based GUI updated the fastest actually, with an average of 6 hours and 40 minutes. Well, their detailed hourly CSV files, which you can see in the other graph, updated with an average latency of 8 hours, 15 minutes. CloudWatch and the cost allocation CSVs were even slower, with latencies of 11 hours for CloudWatch to days for the cost allocation CSVs. And GCE and Rackspace were even slower, with GCE latency coming in over the course of days, with an average of over 2 days, maximum, I believe, of 11. And Rackspace latency typically within 24 hours, but sometimes longer. These graphs show individual instances and their corresponding billing latencies. You can note that the y-axis for the GCE graph is in terms of days, while it's in terms of hours for Rackspace. So the takeaway from this is that all providers take a long time to update their bills, which is bad for any customer who wants fine-grained, timely information about how much they're being charged, or say wants to audit their bills, as we discussed in the last talk. That being said, we are also concerned about high variance in billing update times, which wasn't reflected in these graphs, but was very high in terms of hours or days of variance. We figured if it's going to be slow, it should at least be predictable. So one of the things we did is look into EC2 billing latency in particular to try to understand more about when it updates and if there were any update patterns. To learn about that mechanism, we launched a number of instances, but staggered their start times by 30 minutes and waited to see when the corresponding billing updates would come in. The green dots here show instance start times for several instances in our experiment. It's just a small sample. The black dots show the web-based management console update times, and the red dots show the CSV updates. So you can see here basically that despite the staggered start times, instances were billed at approximately the same time in sets, which would suggest periodic batch processing. At the same time, though, we did not see any evidence of universal batch processing times across accounts or instances or any universal time of day on EC2. The only provider we saw universal update time of day was Rackspace, which is between 9 and 10 in the morning. Shifting gears a bit, the compute billing latency is not the only mystery. One of the other things we're interested in is determining what compute time actually is when we say we're going to be charged for 1 hour of compute time. And you can see there are many events in an instance lifetime, and it's often unclear when billing for an instance begins and ends. And this is especially important to know in the case of providers like EC2 that bill by the hour, and especially if you're running many instances in parallel and want to cut off near the end of an instance hour. So you could potentially get billed twice as much if you expect to run over. And the key problem is that although Amazon tells us that a customer gets billed for a certain amount between when an instance starts and stops, it's not exactly clear what these terms mean. So for example, starting could correspond to the user launching an instance, or when the launch request is serviced in the event that it's queued, or when the instance boot is complete, or when proc uptime registers 0. And similarly, stopping could occur when a user initiates shutdown from within an instance, or when a customer terminates from the management console or an API call, or when termination is complete. So it's still ambiguous on the margins. We did determine the most likely timestamps for each of the 3 providers, but there was still jitter involved, leading to even more unpredictability. And this is partly because to get most of the instance lifetime timestamps, as I mentioned before, we needed to use the provider's API calls to basically poll for instance state and then recorded the timestamps corresponding to state transitions. But that's inexact, of course, because you still have variable network latency, you have variable server response time, And you have limits to polling granularity. In some of the cases, if we were rate limited, polling the instance objects. So all this is to say that basically there's a semantic gap between the provider APIs and the underlying mechanisms, so that the mechanisms in the ultimate billing behavior is still opaque to customers. So we can see evidence of some of the jitter here. And in this round of experiments, we basically tried various combinations of hypothetical start and stop timestamps and terminated an instance, say, delta seconds after our hypothesized start timestamp. So the goal was to determine the start and stop timestamps that corresponded to getting billed for 1 hour at 35.99 seconds and 2 hours when you hit 3,600 seconds. So it's a lot of trial and error. On the y-axis here, we have the fraction of instances billed for 2 hours. And on the x-axis, we have the interval between the instance launch timestamp, which is actually provided by EC2, and the time we issue the terminate API call in seconds. So this was the interval that most closely correlated with the billing outcome for EC2, more than any other interval. But as you can see, there's still variance across 3 different instance types we tried, 400 instances per type. And basically, you could get billed for 1 or 2 hours. There's seemingly no way a customer can control this behavior in advance, short of terminating the instance well before the end of an hour. Okay, we also ran into a few anomalies. This graph shows the amount of time, measured uptime an instance received in seconds along the x-axis, grouped by whether the instance was billed for 1 hour, which is along the bottom, or for 2 hours, which is along the top. So the thing to notice here is that the outlier in the bottom right-hand corner sticks out. So here we have an instance that was terminated 35.95 seconds after it was launched and was billed for 1 hour, but reported an uptime of 37.50 seconds. So it definitely looks like we're getting underbilled here. We were interested in this and created a special fast boot kernel that would boot very quickly in an instance just out of init ramfs and immediately send heartbeat messages to our control server. We then terminated the instances delta seconds after launch, with delta being very low, some number of 15 seconds, 19 seconds, 20. And as you can see here, that for delta of 19 seconds, 4 out of the 20 instances we launched received 2 minutes of usable uptime and were never billed. So this suggests a race condition in the billing mechanisms that allows for free compute time. Now, most people are not going to use this unless they want to create some crazy distributed system that, it's probably not going to happen. But just the very fact that it seems there's a race condition embedded here was definitely of interest to us. All right, shifting gears a bit, I'll now briefly discuss some of the results of our investigations into storage and network billing. Storage can be billed both for the duration of volume allocation, which all 3 providers bill for, and for IOPS, which EC2 bills for. So once again, we found some bugs and some anomalies. In Rackspace, we found that the unsuccessful deletion of a storage volume led to overcharges for block device allocation, so that if a user tried to delete a storage volume before it successfully detached from an instance, the volume would enter an intermediate state where it cannot be deleted or used by the customer, but was still accruing charges. And the only way we got these completely deleted was by calling customer service, and I think somebody literally went to the floor and shut them off. So we notified them about this, and they're addressing it. In terms of IOPS, though, the provider charges based on its view of storage operations, and this is for EC2. The issue is that the level at which these operations are measured may occur outside a customer's view, possibly at the hypervisor level, we don't know. The effect, though, is that any caching or aggregation a provider might do could result in fewer IOPS measured at the level at which they do resource accounting and billing, if the accounting and billing doesn't happen at the same level as the aggregation. So we wanted to test this, and you can see the effect here. Basically, here we performed 1 gigabyte of sequential reads and writes to an EC2 block storage volume, used direct I/O to avoid caching the guest. And the graph here shows the ratio of the number of storage operations that we measured on an instance using proc disk stats to the number of operations that were actually billed by EC2. And as you can see, proc disk stats reports many more I/O operations that were eventually billed by EC2, which indicates some degree of caching and aggregation. And a similar phenomenon can be seen in network billing as well. For EC2, which has the most complex network billing policies, network traffic was typically underbilled by an average of 5.6% for internet outbound traffic, which is their most expensive category. We also observed underbilling in other traffic categories, but not by quite as much. It also did turn out that some rack-space instances were fairly substantially underbilled for traffic that was successfully sent from the instance to our controller on campus, say by as much as 125 megabytes out of 1 gigabyte sent. So that also suggests that there is a bug in rack-space network billing that we're not able to precisely determine the cause of the underbilling. So what does this all mean? I would say that in summary, we found that today's billing systems provide bills only after substantial delay, that the delay isn't predictable, and sometimes updates are not atomic. Key information about billing, such as instance lifetime timestamps, are not exposed to the customer, so they must approximate those timestamps by pulling the API. And that's not only inaccurate, but it's also inefficient for the provider and the customer. At the same time, billing information and related functionality are not available via an API, and thus those are difficult to deal with programmatically. You have to resort to things like screen scraping, which nobody wants to do. So this also means, as Li Chen mentioned in the last talk, that the customer must inherently trust the provider. And it means that the customer, who may not be aware how much he has been billed, cannot use precise billing information for real-time deployment decisions. None of these things are good at the moment. So I'd like to conclude, though, with some thoughts and suggestions for future work. So as we've seen, there's still many aspects of resource accounting and billing that are not immediately measurable by the customer, making real-time decisions difficult. Ultimately, it would be interesting and useful to better understand the exact trade-offs between performance on the one hand and accurate, timely, transparent billing on the other hand. We envision a billing API where customers can programmatically obtain precise information about their bills in real time. And some progress toward this goal could potentially be made now. Some things that seem like they would be fairly straightforward, such as exposing internal metadata, such as the timestamps when billing begins and ends, so that the customer can see the provider's viewpoint of those numbers. Other aspects and limitations may require closer collaboration between industry and academia in order to get a clear picture of the possibilities and limitations for transparent real-time billing. So that's all I have to say. Thank you, and be happy to take any questions.
David Lynn, Vanderbilt University. Did you, by any chance, arrange to have some of your tests run from a peer who was connected elsewhere on the internet?
That is a good question. No, we did not, and yes, that would be a very good idea. So it's actually something that I had not considered. We were obviously working out of University of Wisconsin-Madison, but certainly working with a separately located, some number of locations outside our own would give us more reliable data. One thing I have to qualify with that is these tests were very arduous. So I have to say, because what would happen is that you'd start a test and you had to have a separate account for every single one of these tests because all the billing information is aggregated by account. So if I say started an instance and wanted to send 1 gigabyte of data and stop, or wanted to calculate some amount of compute time, I'd have to start this, and then if anything went wrong, I couldn't use that account for several days because you have to wait until all possible information had been flushed out. So first of all, if you have a typo in your Python script, you're done for. You have 2 days. And in general, this definitely limited the amount of experimentation we're able to do. So that's definitely a great idea. But yeah, we're somewhat limited by the pace our experiments could go.
Can Türkişçi from IBM Research. The billing issue is a tough issue, and I was curious how you approach this. I think one possible pitfall here is you are trying to kind of correlate guest OS-based measures to billing, and I was wondering whether you think this is the right strategy, because like you said, there's caching effects, there will be timekeeping effects, so the resource consumption you see is not the resource consumption the provider actually sees. So I'm thinking maybe one interesting aspect of this is actually see if you can replicate the infrastructure on your side. Let's say for EC2, build a simple Zen-based environment, and maybe for Rackspace, make an OpenStack-based environment, and see the measures you see inside the guest actually mean exact resource consumption on the host, because that's what they use. And like for actually AWS, CloudWatch also gives you some of these measures from the host side. So maybe those are more reliable to do such estimates. Mm-hmm. So I was wondering whether you were like going towards this direction, or have you thought about this?
We had thought about it somewhat. Kind of our angle, I would say, was that the thing we would like to see the most is basically to see provider interfaces exposed to the customer. So they essentially say, this is what we're seeing. We're seeing these timestamps. We're seeing this number of IOPS. Amazon, so far, has done the best job at exposing those statistics, for sure. But they could still even provide more, such as all the instance starting and stopping, all the instance state transition timestamps. GC actually does provide a few of those. What you're suggesting about reproducing the infrastructure is actually, it's a good suggestion. I don't know how feasible it could be. As I think it was one of the things speaker spoke about yesterday in the pitfalls of cloud compute research, is that it's difficult to reproduce a lot of these because we just don't have tens of thousands of machines in the same. And also, it's one of the big things we saw here is that just the actual billing mechanisms are essentially a black box. So we don't know how they're doing this. You can see that, okay, it's probably batch jobs. It's probably roughly in 6-hour intervals. But those are still closed off. I think one avenue that would be really interesting is if any of these providers would be interested or willing to collaborate with academia.
Yes, so your second point, the black boxness of billing is a very valid concern. So I think you are spot on there. The first point, I had a more humble suggestion. Basically, can you check that the resource measures you see inside the guest OS are actually reliable by looking at not a big scale system, but 1 or 2 host system where you can look at from the host side, because that is generally an issue. And that might be a misleading measure to rely on for resource accounting and therefore billing. That's what I was thinking.
Okay, yeah, I misunderstood the first point. No, that makes a lot of sense, and that would be a good next step to take. Definitely, thank you.
Hi, this is Ritesh from VMware, and I have multiple questions. So to start off with, the first question is, if you view billing as a statistical process where they're trying to estimate how much you have used, did you see any measurable difference in the actual dollar amount charged because you are underbilled as well as overbilled?
No, so we were never overbilled, except in the case of the Rackspace hanging disks, which wasn't so much a billing problem as it was, their disk provisioning issue. So I think, after the fact, I spoke somewhat casually with some of the AWS people and some others. And one of the things, one of the impressions I get is that actually performing resource accounting in a real-time setting at very high granularity and being able to report this stuff in real time takes an enormous amount of hardware. And that in order, the kind of cost-benefit trade-off economically for them, and this is just my impression, I don't know if this is actually the case, but that the cost-benefit trade-off would make them want to slightly underbill and throw a lot less hardware at it. So that's the impression I get. Still, that being said, I think there could be a lot of steps taken towards still exposing what they do, in fact, do to so the customer.
That was actually one of my questions, is that if you have any estimate as to if they were to accurately bill, because it's a distributed system problem, and the more accurate you want to give, you have to trade off something else. So,
yeah, well, that's definitely, it's one of my big questions too, and I think if Amazon or any of the other cloud providers are open to collaboration, that would be a very interesting topic to look at, precisely what these trade-offs are.
All right, thank you.
Thank you.